Next, we want to talk about what happens with non-atomic messages. In other words, a transaction starts, but before it can finish, another transaction begins and gets in the way of the first transaction. So here's a case that we see on this diagram. The first step is that A sends a read request to the home. The home responds with data, but the message doesn't arrive yet because maybe the network is congested. B sends a write request to the home. The home, because the home has received a write request, it needs to invalidate all current sharers, so it sends an invalidation to A and it arrives before the reply D. Well, this is a problem. Why is it a problem? It's a problem because A has just received the data from the home, but that data is no longer valid because in the interim it was written to by B. This is called an early invalidation race. So A needs to respond in an intelligent way, but the first two obvious ways are wrong. The first is that A could reply with invac, so it just acknowledges the invalidation, and then B thinks its write propagation is complete. But that message from H to A is still outstanding, and when it is received, A would put the block in its cache, but the block is no longer valid. In fact, it has just been invalidated. So invac won't work. Another way that it could be handled is A just ignores the invalidation message, but that's no good because A now has out-of-date data and it thinks it's valid. So both of those are incorrect. In the last case, write propagation has failed to occur. So there are two possible solutions to this. The first is brute force, where the home waits until it receives all the acts that are outstanding. And the second is for the home to keep track of, or for the node to keep track of messages that are outstanding. It keeps an outstanding transaction buffer, and it does not process any requests to that block until the current transaction is completed. So now I've got a few questions to ask you about these scenarios, and let's scroll back to the diagram so you can see it while you answer. Now let's look at what happens when a read request is processed. We'll consider two cases. First, read to a clean block, and second, read to a block in EM state. With a read to a clean block in the home-centric approach, the directory enters a transient state because it is waiting for the transaction to finish. The home replies with data. The requester receives the data and sends the act to the home. The home closes the transaction, which means it transitions to a stable state and updates the sharing vector. If another transaction begins at that time, the home will not process it. Or I should say, if another transaction begins while the home is waiting to close the transaction, it will not process the other transaction until the previous transaction is closed. Now, disadvantages of this are too much serialization at the home node. The transaction lasts longer than it would if the requesting node participated in doing the synchronization, and it requires an ACK. So now let's look at the requester-assisted approach. And you see here in the diagram, it shows you with the home-centric approach, you need to wait for all of these steps. You need to wait for the read to be received by the home, the reply D to be received by the requester, and then the home again to receive the ACK. With the requester-assisted approach, the only time that other transactions need to be stopped are right here while the home is processing the information. The directory would send a reply D, and then immediately after sending the reply D, it would close the transaction. It relies upon the requester to either buffer or NAC all new requests until the reply ID is received. In other words, until the current read transaction is completed. So the requester might have an outstanding transaction buffer, as we've just suggested, and in that case it holds on to all of these other requests until the read transaction is completed, or it might just NAC them. It might just say, oh, sorry, try later, and then the other node that's trying to cause a transaction to be performed has to wait until this one is done. But in either case, the requester is in control, and because it's in control, there's more overlapping of processing that's possible. Okay, so the second case is a read to a block in EM state. And in this case, we also deal with the home-centric approach and the requester-assisted approach. With the home-centric approach, the requester sends a read request to the home. The home again enters a transient state, and this time it sends an intervention to the owner because it doesn't need to purge that block from the other caches. It just needs to have them change to shared state. The owner then flushes data, or flushes the block both to the home and to the requester. The requester then needs to confirm that it's received the block by sending an ACK back to the home, and then the home closes the transaction, which again means that it transitions to a shared state and updates the sharing vector. So all of that has to happen before any other transactions to this block can be entertained. On the other hand, with the requester-assisted approach, what's the same as before is in green here. So the requester sends a read to the home just like it did before. The home enters a transient state and sends an intervention to the owner. There's no difference there, but the home can't close the transaction yet because in the final state it needs to have a clean copy of the block, so it stays in the state where no other transactions can be entertained, and then the owner flushes the block to the home and the requester. Upon receiving the block from the owner, the home closes the transaction. So the home can close the transaction here. It doesn't have to wait for the requester to receive it and then respond and the home get the acknowledgement, because we're depending upon the requester to serialize transactions.